This is Physics 2211, Lab 4 Oscillations. So introduction. Purpose of this lab was to track and model the motion of oscillating spring mass system. We tracked a spring in the video that was connected to a point, and it was an oscillating spring mass system. So we want to gather the x and y data. We wrote code to simulate the forces that would have been acting on the spring, and then we want to compare the graphs of the tracker data and simulation data, see if they're similar. And then we also want to see if the model followed the energy principle, which is that change of energy is equal to 0 because our spring in the earth was the system. For the graphs, we want to see that the total energy stayed at 0. Yeah. So concept used in this lab, Newton's second, force equals ma, and then we also have Fnet, which was going to be equal to, or is also part of Newton's second, which is force of spring plus force of gravity. We have force of gravity is negative mg, and force of spring 1/2 k squared. For the energy principle, change in E is going to equal to the work done in the surroundings. In our case, we bundle everything up into the system, so the work by the surroundings is equal to 0. So change in E should have been 0. And we have a velocity update and position update. So tracker stuff, this is what our tracker looked like. So here's the video, and we tracked the position of it. So you can see it's oscillating, it's going circles, going up and down. You can see that the graphs here are waves. So coding, how do we code the spring in WebPython? So we had a video that we used in Canva, which was the video you saw in Tracker. And within the video, we were given some initial conditions that the ball mass was equal to 0.402, and that the spring system stiffness was going to be 6.875, and the relaxed length was 0.127. Our initial position was what we got off the tracker. So yeah, and this is everything here. So coding. So this is the way that we're going to compute our energies. So we have kinetic energy, gravitational potential, and spring energy. So kinetic was going to be 1/2 mv squared, and then we have universal gravity, which is going to be ball mass times g times the ball position, and then we have the spring, which was 1/2 the k, the stiffness, and then s squared, and then our total energy was going to be all of them combined. So coding, and this is the coding loop that we use to build the trajectory. So we found f grav and f spring to find the f net, so we can model the trajectory of the spring mass system. We use velocity and position update, just like lab 3211, and then we calculate the energy changes so that we can see the graph and the energies, so that we can see that the change is equal to 0. So that's what we're doing right here at the bottom. So results, here you can see that the tracker is the blue, and the red is going to be the experiment, or is our tracker data. So our tracker data is red, and then blue is going to be our coding. You can see they're very similar to each other, however they're just a little bit off, and this could be the reason for this could be like drag, and there's other things. Ideally we put everything into the system, however it's not possible in real life for us to do that. So there's other things acting, contributing work, which is the reason why you see these deviations. Another reason why for error could be that tracking was hard. It was a pretty small thing, so it was pretty hard to track. So is the energy principle satisfied? Yep. Energy principle here is satisfied. As you can see here, the energy delta E is going to be the orange line, and throughout this entire graph you see that delta E is a constant line on 0. And what does that mean? That just means that the change in E was equal to 0, and yep. So basically in the energy principle we said that change in E was going to be equal to 0, and this satisfies the energy principle. So yeah. Discussion, which was comparing the oscillation periods. So here we can see this was the oscillation period for X, here's the oscillation period for Y. The X was for 1.692 seconds per oscillation, Y was 1.5 seconds per oscillation. So yeah.